The purpose of this presentation is to introduce you to the idea of solution reactions and how we deal with them. Before we can do this, we need to get some preliminary vocabulary under our belts. The first term we need to be familiar with is aqueous, which means to dissolve or dissociate in water to form a solution. Most of us know what it means to dissolve, but dissociation is something different. It's where the ions of an ionic compound separate, and this is often caused by water in aqueous solutions because water is able to disrupt the electrostatic attractions between the um, ions. The complete ionic equation is a balanced chemical equation where all soluble ionic compounds are dissociated. It's both mass and charge balanced. So essentially, once we know that something is aqueous, when we write the complete ionic equation, we are going to separate them. Spectators are just things that are in the complete ionic equation that aren't involved in forming product. Remember, for solution reactions, in order for them to happen and not be labeled as no reaction, we must form either a solid, liquid, or gas. So any participants that either start as solids and end as aqueous or liquid or gas, or anything that goes from aqueous combines to make a solid, liquid, or gas, would not be a spectator. Those things that are not involved in that process are the spectator. And finally, the net ionic equation is the BCE, or balanced chemical equation, showing only what happens chemically in the reaction. All spectators are eliminated and ignored. So why are we doing this? Well, reactions in solution contain reactants and products that are soluble in the solvent. If we're talking about aqueous systems, this means we're talking about water. These soluble participants always have, in a water system, the symbol AQ and should be dissociated if they're from an ionic compound. When they dissociate, they separate from each other, like we said before, but here's an example of that. NaCl aqueous is really more aptly written as Na plus Cl minus, both aqueous. Those ions are surrounded by water and are no longer in contact with each other. Two important things to note about dissociation. It only occurs for compounds that are considered soluble according to the solubility rules. If you don't have them in your head, look on your sheet or in your textbook. Now, this is not totally true. It is going to happen for essentially every ionic compound, but it's only going to happen to an appreciable degree for things that are considered soluble. And it really is more of a chemical process than a physical process. The separated ions are going to behave differently in a chemical sense than the compound they originate from. So it's not like melting ice. That's a physical thing and we just kind of ignore it. It's not the same. It's not the same as taking sugar into water. Sugar into water really just spreads out into the water. It doesn't separate. So the reason it's different is with these ionic compounds, once they separate, they're now free to move around and find new partners, like in a metathesis reaction, where they can find another partner to bond with and produce something new. All right, so the purpose of doing this is to focus on only the chemical reactions that produce products. To do this and to focus on those, we're going to follow these simple steps. First, we're going to write a BCE, or balanced chemical equation, for the process as shown below. If I react potassium chloride and silver nitrate, this is a metathesis reaction, and I know I'm going to produce potassium nitrate and silver chloride. Next, I need to consult the solubility rules, hopefully these are in my head, to determine if there are any solid products produced. If there's gases or liquids produced, I would be expected to know common liquids and gases. Water is the most common liquid we're going to form. Gases would be things like carbon dioxide, sulfur dioxide, hydrogen gas, nitrogen gas, common gases. So if I do this for the above equation, I'm looking at potassium nitrate and silver chloride. Well, the solubility rules say that all nitrates or all group 1A cation compounds are soluble. So either way, potassium nitrate is aqueous. Silver chloride, however, is a halide compound, and halide compounds are soluble except with silver, lead 2, and mercury 1. So silver chloride then is solid. I'm going to then dissociate all aqueous species to form the complete ionic equation. So since KCl, AgNO3, and KNO3 are aqueous, I'm going to split them, K plus Cl minus, etc. And that's going to produce for me my complete ionic equation. Note that silver chloride is not split. It forms a solid compound, so it remains together. After that, we're going to cancel out all spectators, just like we do in algebra. And all we mean here is species that are the same number and same state on both sides. They don't change at all from one side to the other. So here's my complete ionic equation again. Notice that I have K plus, one of them on each side. They cancel out. I have NO3 minus on each side. And so those are the only things that aren't participating. So once I've eliminated them, I'm going to rewrite the equation only with the ones that react chemically to form the net ionic equation as shown below. Notice above only silver chloride and silver chloride remain, so they end up in the net ionic equation. This is typically employed for single replacement and metathesis reactions. It allows me to know exactly what's going on chemically in the system, and it is also used quite effectively as a lab technique to isolate and separate ions from each other. It's also used in water treatment to remove heavy metals from water samples. Remember, again, just to make sure we're clear, for this reaction to occur, I must produce at least one of the following: a solid precipitate, a pure liquid, or a gas. No reaction is an option here. If I don't produce one of those things, I go no reaction. So here's a sample problem with a single replacement. Sodium metal reacts with aluminum chloride. So we know it's single replacement, so we should know that the idea is that sodium and aluminum, both being metals, can potentially swap places. If I consult my activity series, I see that sodium is very near to the top and will replace aluminum. So this is my translated system: sodium solid plus aqueous aluminum chloride. They're going to trade. I know it's NaCl based on the charges, Na plus 1, Cl minus 1, and aluminum comes out. So balancing the equation requires 3 sodiums and 3 sodium chlorides. And now we need to determine states. All halides are soluble except silver, lead 2, and mercury 1. Sodium is not one of those, so it is aqueous. And aluminum metal is solid. All metals are solid at room temperature except mercury. We're going to form the complete ionic equation by separating species out. Notice they keep their charges, and any subscripts become coefficients on the individual ions. Like AlCl3 generates 1 Al3 plus and 3 Cl minuses. Now we're going to cancel spectators. Chlorides are spectators, and that's it. Sodium goes from solid to aqueous. Aluminum goes from aqueous to solid. They are changing states. They are not spectators. So we write our net ionic equation, which says that 3 moles of sodium react with 1 mole of aluminum ions to produce 3 moles of sodium ions and a mole of aluminum. Next sample problem is metathesis. We're going to react sodium hydroxide with iron 3 chloride in solution. This means that we're going to be operating with both of these aqueous. Sodium hydroxide and iron 3 chloride are both aqueous to begin with. The products I produce when I swap them: NaCl, again based on swapping charges, and iron 3 hydroxide negative 1 makes FeOH3. If I balance, I'm going to need 3 sodium hydroxides and 3 sodium chlorides to complete the reaction. Determining the states, again, sodium chloride was aqueous before, it's aqueous now. There are very few hydroxides that are not insoluble, and iron 3 hydroxide happens to be an insoluble one, so it will produce a solid precipitate, so the reaction will happen. We form the complete ionic equation by dissociating all the aqueous things. Sodium hydroxide, iron 3 chloride, and sodium chloride all dissociate. Again, carrying out coefficients to each member, and any subscripts are added into the coefficient as well, or multiplied into the coefficient. Next, we're going to cancel the spectators. The sodiums are gone, the chlorides are gone, and all that remains is iron and hydroxide. So my net says that 3 aqueous hydroxide ions react with an iron 3 ion to produce FeOH3 solid. One final metathesis example just to show you why we have to be worried about what states the products are in. If we go with this sodium chloride reacting with calcium bromide in solution, we begin with 2 aqueous halide compounds. We're going to swap partners so that we now have sodium bromide, calcium chloride. Swapping charges gives me the formulas. We balance, requiring 2 sodium chlorides and 2 sodium bromides. Determining states, there is a typo here. Let me fix this. This is not solid. Calcium is not lead, mercury, or silver, so it stands no chance of producing a solid. So if everything's aqueous, then I dissociate all aqueous species, which means I dissociate everything. Next, I cancel spectators. Sodiums are gone, calciums are gone, chlorides are gone, bromides are gone, and guess what? There's no reaction. There's nothing left to produce any product. We didn't form a solid, liquid, or gas. So again, this is an option. Be aware of that.